Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. What did we start talking about last time? kNN. Okay, what is kNN? K-nearest neighbor. Okay. What does that mean? Is it a classification algorithm? It's a classification, right? kNN is classification or not? Clustering. No. We didn't talk about clustering yet. Okay? We'll talk about clustering inshallah hopefully today. But kNN is for classification. Right? What is the main idea of kNN? Fatma? Yes. And what do you mean by surrounding ones? Yes, to the closest ones. Right? The closest ones. So if k is 3, then we will look for the closest 3 points or 3 vectors in the vector space. So we assume that every example is a vector. We represent it as a vector in the vector space and compute the distances and find for k equals 3, we find the closest 3 vectors or points in the space to the test point. And when we get these 3, what will happen? We get the majority label from them, right? And that will be the label that we predict for the test point. Right? Do you have any questions about what we covered last time? Right. I think we stopped here when we were talking about, or we were about to talk about decision boundaries. We started by looking at what we call Volanoy diagrams. So what is a Volanoy diagram? For each point in the space, in the training examples, there is a region in which every point, that point will be closest to it. Okay, so this is like the owned land or owned region for that point. Okay, so for example, if change this, if I'm talking about this area, for example, any point in the gray area here, because k is 1 here, you will find this point the closest to it. Even if it's very close to the boundary here. Okay? If there is a point here, still this point is closer to that, closer than that, and closer than that, and so on. Okay? So we can see a region around, or the neighborhood, a neighborhood for each point. Okay? And we also saw that when we increase the points, these regions will get closer. These regions will get closer, right? Because they will be very close to each other. So for example, here, you will see that this area now is just the area where I can classify or predict the label for any point to be light green. Okay, because any point here will be closer to that point. Okay, right. Now, imagine instead of giving a different color for each region, we will color the region by the label of the point. Let's assume that we have just 2 classes, 2 labels, okay, green and red. So every region will be labeled by either green or red. So we'll only have in the entire space, we'll only have 2 colors. Okay? Right. Now let's assume that all the right side points will be from the green class, and the left side points will be in the red class. Okay, imagine now this happens. How many regions we will have? In this case, just 2, right? To the right side we'll have all green, and to the left side we'll have all red. Right? And in between, we'll have something like this boundary, right? This will be the boundary between these 2 areas. Right? To the right of it, it will be green, and to the left of it will be red. Which means that any point, any test point that will be located to the right of this boundary will be classified as green. And any one that will be located to the left of that boundary will be classified as red. This boundary in this case, which will be in between, is called decision boundary. It's called decision boundary. Okay, so in general, decision boundaries are boundaries that separate the classes. So on one side there will be a class or a region for that class, and on the other side there will be the region for another class. Okay, so here's another example. Let's say that we have these points to be from the blue class, and these points will be from the red class. So, and a decision boundary can be something like that. It will separate the red from the blue. So any point that is out of this boundary is red, and any point inside will be blue. Okay, so that's an example, of course, of a decision boundary. Okay, so you got the idea of a decision boundary. It separates regions of different classes. Right. Can decision boundary be really complex or just simple as we see here? Of course, it can be very complex. It depends on the model, it depends on the values of the parameters and the hyperparameters. So it can be very simple as a line, or it can be very complex, as we will see. Right. Why is this useful? Why the decision boundary is useful to study or to understand? Two reasons. First, it will help us separate the areas. See in the feature space where the positive examples are located and where the negative examples are located, and how we can separate them. So it's good for visualization. Okay, to see if these points are separable or not, and how they are, we can separate them. It helps also visualize the complexity of the model. As we said, some models will be like a line or a curve, very, very simple. Some models will be very complex, as we will see in the next slide. Okay, so it is good for visualization and also to understand something about the distribution of the data that we have. Right. For kNN, how can we see decision boundaries? Let's here assume that we have two classes only, green and red, and these are the points that you see here, and assume that k is 1. When k is 1, every point will have its own neighborhood, right? So for example, if you take this point, you see the region around this point, very small, right? Why is it very small? Because the surrounding are green, so whenever you get outside this region, the closest one, because k is 1 here, the closest one will be green. But inside that small region, the closest one will be that red one. So the region is very small. It's like a very small island. Okay? Similarly here, although the neighborhood is majority red, but because k is 1, when we have k to be 1, that means that we will only consider in prediction, SLM, we will only consider the closest one. Only the closest one will affect our prediction. Okay, yes. Sorry? No, of course not. K is a hyperparameter. We can change it. So K is not a constant. I mean, it's not always 1. It can be any value that we can tune, as we will see, inshallah, maybe in 5 minutes. Yes? It's not selected. It's constructed based on the data. Okay? So you will see here, Did you understand how Volanoy diagram looks like? It is similar here, but coloring the region with the color of the class. Yes, because k is 1 here, every point, its own neighborhood is very small. Now, how can we get larger areas when there are side-by-side regions that are of the same color? Yani here, each neighborhood of a point is really small, but they are all combined because they are all green. But here, this is a small island. This point is like an outlier. It is surrounded by all greens. So its own area is not combined with others because its own area very small, it's red. Okay? Did I answer the question? Okay. Any other questions? So this happens when K is 1. We have multiple small islands like that. Yes. Yes. Yes, because we didn't talk about in Volanoy in general. Volanoy in general is not about classes. It's just to show you the regions of effect. But here, we are coloring the regions by the color of the class. Okay? And thus, the regions that are side by side, that are next to each other, they will be combined in a bigger region. Okay? Is that clear now? Type. What do you expect when we increase K? Which, yes? Number of small islands or number of will get smaller. Why? Exactly. The decision, the label will not be based on just one, will be based on more. Okay? So let me show you an extreme, not a very extreme, but a bigger value of K. K is 15 here. Same data set, by the way. It's the same data, same points. Okay? But now, because K is 15, these small islands disappeared. Why is that? Why is that? Now let's get to this point. You see this point here? It has its own island, right? Let's look at it at the same point here. Why don't we have an island around this? Because now K is 15, right? So if we have a test point that is very close to the red point, it will look at 15 closest points, not just one. And of course, when we look at 15 points around this point, we'll see that the majority is green. So the area of this point is actually green. The area surrounding this point is green. So all of this area now, any test point in this area, the 15, if we look at the 15 closest points to it, we'll find the majority will be green. So this island disappeared. Similarly here, all of these islands disappeared. Why is that? Because the majority is red here. They were having green islands because K was just 1. So each one is affecting its area. But now each one of these has almost zero effect on its area because it is surrounded by a majority of the red points. Okay? Is that clear, the difference? Yes. Yes, they don't exist anymore. They don't exist. Now, what is the meaning of these areas? When we look at this, these are decision boundaries, by the way. These are decision boundaries, which means that if a test point is located here, it will be predicted as green. If a test point is located here, it will be predicted as red. If a test point is located here, red. Here, green. Okay? So that's the meaning of the decision boundary. Now, when we have K equals 15, any point above this boundary will be labeled as red because we are looking at 15. Whenever we look at the 15 closest in this area, you'll find the majority is red. The majority is red. So this whole area is red. That means that the effect of this small number of green points is this has disappeared. Okay? Has completely disappeared from the classification, from the prediction. Okay? I saw a hand. Yes. What is better accuracy? You mean when K is 1 or K is 15? We'll talk about it in a few minutes. Okay? Type. You understood now why this is happening, right? Type. Which decision boundary here is simpler and which one is more complex? The one on the left, is it complex or simple? Very complex because it has so many boundaries actually. It's not just one. But this is much simpler. Okay? So this one is more complex. Type. If you look at this one, does that remind you of something that we discussed earlier in the course? When we have looking at the very small details, right? Looking at individual examples when we make decisions. What does that mean? Yes. Overfitting. So that's an example of overfitting here. Okay? Overfitting. We are learning to the level of each example. We are not looking at the big picture of the data. Okay? We are looking at very small details in the data, even to the outliers. It seems like this one is an outlier, right? We are giving it its own region. Okay? This is overfitting. Right. Now let me ask you another question. If we increase, let's say that we have 100 points in this data. Okay? 100 points. What happens if I took k to be 100? We will have one color, right? Why is that? Yes, we will not even have a boundary. Everything will be the same region, the one region. Why is that? Why is that? Why did you say one region? Yes, why? I understand. So in this case, let's say that it will be green. Okay, when k is 100, it will be all green. Why? How did you know it will be green, for example? How did we pick green, not red? Okay. Still, I didn't get the reason. Why we will have just one region? Yes, my son? Yes. When k is 100, what does it mean to have k is 100? Whenever we have a test point, we'll get the closest 100, right? 100 is the whole data, right? So we will just look at the majority label of the whole data for any point in the space. Anywhere, put the point anywhere, the closest 100 will be the same points. Okay, so we will have the same label for them. If the majority is green, it will be green. If the majority is red, it will be red. Okay, type. What do we call that? Underfitting. That's the other extreme. Because that now, we didn't learn anything from the data, right? We're just giving the label of the majority for every point. Whenever the point or wherever the point will be located, we'll give it the same label. So we are not actually learning almost nothing from the data. Just learning something which is the majority label, which we'll give for every test point. Okay, so on one extreme, it will be kind of overfitting when k is 1. When k increases very large to the extent of the number of points, then we'll be underfitting. So it seems like we should have k somewhere in between, right? Okay. Now, since we saw that k is important, right? Is important in making the classifier good or bad. So we'll have to tune. K is actually affecting the complexity of the of the space, of the hypothesis space, okay, of the decision boundary. Here, the space is very complex. Here, the space is is less complex, okay? And as we increase k, the complexity will decrease, okay, to the extent that everything will be just one region. Right. So higher k yields smoother decision boundaries. We saw that, right? This one is smoother than this one. Right. If that's the case, then how would we set k in practice? That's your question. How would we get the best value of k? Mariam? Yes, we tune it as a hyperparameter. That's a hyperparameter. It's nothing new here. Okay, k is a hyperparameter, and we know how to tune hyperparameters in general. Okay, we'll have to have the training, div, and test splits. Train the model on the training set. Actually, in kNN, we don't do any training. Get the best value of the hyperparameter from or using the div set, and then apply it to the test set. Okay, so we'll use the div set, of course, to tune this because k is a hyperparameter. Okay, this is very similar to what? that we discussed earlier? Which hyperparameter we discussed earlier? The depth of the decision tree. Okay, it's the same thing. Yes.
In this case, will we increase the percentage of the
What do you mean by increase? Usually we said it's like 70, yes, around this 70, 10, 20.
Yeah, so now we set 70 for the
Training?
yes, but there is no training.
Yes. No, but this, okay. So you are saying, Yani, it's kind of waste, right? We are wasting 70%. Is that the case here in kNN? Is it the fact that we are not doing anything in training, does it mean that the training set is useless? Why not? Why not?
It's storing all the data.
Okay, storing them, but are we using them?
Yes.
Where?
When we are doing the parameter thing,
In testing. We are using them in making predictions. So we need them. We didn't use them in training, but we use them in testing, in predictions. Okay, so you cannot just say that this 70% is useless and increase the depth set. No, it's still. Without the training examples, we will not make any predictions. There's no data to get the smallest, the closest one. Yes.
we can say that while training, we are actually making those circles. So
Ah.
kind of like make circles would be equal to what easier because we just have to make circles with every point. And in case of a higher K, we have to use computational power in order to do the analysis.
Okay, very good question. So your question is, maybe with small values of K, it will be simpler to make predictions, right? But you didn't say it's simpler to make predictions. Say it's simpler to draw the circles, right? Are we actually drawing these circles? What do you think? These are just for visualization. This is showing you how the algorithm actually works. But we will not draw these boundaries. We will classify based on the algorithm. And you saw the algorithm doesn't need to determine exactly what is the decision boundary. Okay? So these are implicit. These decision boundaries are implicit. Okay? So this is one. Second, as you saw, when K is 1, this is overfitting. This is like memorizing every single example. And that's not good. Okay? But the best value of K still for your problem will depend on the tuning that you will do. So we'll have to find, for one problem, maybe K is 3 will be good. For the other, K is 20 is good. So you have to tune it. Okay? Yes. Sorry? You mean in terms of time? Which one is taking more time? What do you think? What are you comparing with? What are you comparing here? No, between what? Okay. Oh, increasing K. Type. When K is 1 versus when K is, let's say, 20. Which one will take more time? It depends on how you will. Yeah, first you have to compute the distances to all data points. Okay, regardless of the K. But then you will get the top K. Okay, so the algorithm of getting the top K, if you I don't know if you study, I think you studied in data structures, heap sort, right? Heaps, okay, are good to get the top from the list. So asymptotically it will be the same complexity. Doesn't matter much. Okay. Any other questions? You have a question, right? Yes. You were asking. Or you have a question. Someone has a question here. In this region, in this decision boundary, on the other side of it, there is a question. Yes. It's general. It doesn't depend on what the model that we are using is. It is general. Okay, so it's the same. Doesn't depend on the model. Okay, and if you look at the slide that or from the textbook, you will see that the approach doesn't depend on how the model actually works. It's like a black box to it. Okay. Any other questions? Good questions. I mean, all of them are good. Yeah, I'm not looking only for good, but actually all of them are good. Okay, right. Now, what we studied so far is just the standard kNN or vanilla kNN. That's the basic algorithm for kNN. There are, of course, some variations. We'll discuss two today. The first one is called weighted voting. What is weighted voting? In standard or vanilla kNN, we look for the k closest examples, right? Did we treat them differently? No, we just get the votes from every one of them equally, right? We don't look at where they are. The fact that they are within the closest 3, خلاص, or the closest 5, we'll consider all of them equally. We don't look at how far they are from the test point. In weighted voting, we give more weight to the points that are closer to the test point. For example, let's say that I have k is equal 3. Okay, and we saw that in the previous lecture. K is equal 3, so I look at the closest 3. Okay, in the closest 3 I found 1 red and 2 green, so I will predict green, right? Right. What if the 1 red is almost on top of the test point, and the 2 green are really far from it? I didn't consider that, right? I just took the vote equally from all of them. But in weighted voting, I would give higher weight to the red point. Maybe because of that, the prediction might be red, based on how we actually give the weights. Okay? So, an extension of the standard kNN is to give weights to neighbors. Now, of course, the higher, the closest the point is to the test point, the higher the weight, right? So we should not use the distance. We should actually use the inverse of the distance, maybe 1 over the distance as a weight. So if the distance is really large, then the weight will be very small. If the distance is very small, then the weight will be large. Okay, so that's it. This is weighted voting. Another variation. This is not now called kNN anymore. It's called epsilon ball nearest neighbors. What is that? Instead of using k closest points, we will determine in advance a region, specific region surrounding the test point, and look at all the points within that region. Yeah, for example, I will say, okay, give me all the points. I want to consider the points within 0.7 from the test point. All the points within 0.7 from me, from the test point, I will consider them in predictions, regardless of how many are they. So if they are 1, then I will take the prediction. If they are 7, I will take the majority. Okay. So for every test point, I might consider different number of examples. This is different from kNN, right? In kNN, I always consider k points. Here, it is different based on the data that we have. Type. So we don't have k as a hyperparameter, right? In this case, but we have another hyperparameter, which is this threshold, right? There is a region, right? Right? It's considered by the threshold where I consider the points. So here it's called epsilon. So if the distance between the test point and any point is less than or equal to epsilon, which means that it is closer than epsilon, then it will be considered in the voting. Okay? This is epsilon ball nearest neighbors. So we don't have k as a hyperparameter, but we have another hyperparameter, which is epsilon. So we should also tune here, right? But tune another parameter, which is epsilon. Is that clear? Any questions? Okay. Now, let's talk about some issues with kNN. Last time, I think, in last lecture, we talked about some advantages of kNN, right? What are the advantages of kNN that we discussed? Does it have any advantage, or it's always bad, kNN? Yes. Fast in training. Actually, it's extremely fast, right? We don't do anything. So training is fast, which is a big advantage, right? Right. How about explainability? Does the decision made by kNN explainable? We can explain the decisions made? Of course we can, right? If let's say if k is 3, then we can, of course, the model can give me the 3 closest examples based on which the decision was made for this test point. So I can look at why the model actually made this decision. So it's explainable, of course. Another thing, it's really simple, right? Very simple. It's huh? Is that an advantage? Yes. It's no. We are not losing any information from the data. Yes, that's another advantage. Yes. Yeah. Sorry. That's not an advantage. Is it slow? You mean in testing? Yes, we said that a disadvantage is that it is more expensive, at least in testing, because we have to compute the distance with all the examples. But here we will discuss other issues with kNN. Right. First, before we talk about the issues, what is the inductive bias of kNN? Have you heard about inductive bias before? Multiple times, right? What is no? What is inductive bias? What do you mean by inductive bias in general? Of? Really? The understanding of the model of the training data? What do you mean by that? Yes, Fatima? Okay. Can you give more concrete definition? Type. What was the inductive bias in decision trees when we use a specific depth? What was it? We are assuming, I was looking for this word, assuming that it is enough to ask maybe 3 questions to predict good, to make good predictions. Okay? That's an inductive bias, an assumption. So it's an assumption that the model has even before the data arrives, even before seeing the data. Okay? So without looking at the data, that's the assumption. Right. For kNN, what is our assumption? Sorry? Is K an assumption by itself? What is the assumption? What is the basic assumption here when we apply kNN, regardless of the value, the specific value of K? There is an assumption here. What is the basic idea of kNN? Not just we have. Why do we have regions, Aslan? Simpler than that. Okay. Sorry. Not the neighbors are near. The neighbors are what? Huh? Sorry? Very good. Which means the neighbors have the same labels. If two examples are similar, then they should have the same label. That's the assumption. Right? That's the assumption based on which the model is working. Why do we give when k is 1, why do we give the label to the point of the same label of the point that is closest to it? Because we assume that they should have the same label, right? So closest points should have similar labels or the same labels. That's one. That's one. Okay? So nearby instances should have the same label. There is another one, which is all features are equally important. All features are equally important. What do we mean by that? Let me ask you about decision trees. In decision trees, are all features equally important? In making the predictions. Here we are talking about making the predictions. When we make the predictions in decision trees, are all the features equally important? No. How did you know? Yes? Yes, in some branches, some features are not there even. And the features are also ordered from the root, right? So the highest one is given higher weight, right? Higher importance, because based on which we make the first decision, which will affect the consecutive subsequent decisions, right? So in decision trees, not all features are equally important, of course. But here, in kNN, all of them are equally important. Where do we see that? What are the features of kNN? It's not the features of kNN, it's the features from the data. This is what we, features here are the attributes of the data, okay? Not the features of the model, okay? Features here means the attributes of the data, okay? Whenever we say features in machine learning, it is features of the data, not the model. Where do we see that in kNN? Where can we say, okay, because of that, yes, kNN is treating all features equally. kNN doesn't give different importance to different features. Where do we see that in kNN? How is that related to features? How is increasing or decreasing k related to features? Look at the algorithm itself. Remember the algorithm. Recall the algorithm. Okay. What do we do when we make predictions? I gave you a test point. How do you get the prediction? How do you predict the label for it? Get the nearest, right? Okay. How do we get the nearest? Calculating the distance. How the distance is calculated? Where are the features in kNN? The features appear in the distance function, right? Only. Once we compute the distance, based on the distance, we will make the decisions. But the feature values are seen only when we compute the distances. Remember Euclidean distance? How do we compute the Euclidean distance? For each dimension, we get the values, we subtract them, square them, and add the others, right? What are these dimensions? These are the features, right? Each feature is a dimension, right? Each feature is a dimension in the vector space or in the feature space. We call it actual feature space because each dimension, we used to say x, y, and z, right? In linear algebra. Here, the x, y, and z are the features. Okay, so in one dimension, in the first feature, the value is 0.3. Second feature, the value is 3.7. And the third feature is 10.4, and so on. Okay, so these are the feature values. Now back to our question. Where do we see them are equally important? Because of the way that we calculate the distance. Do we give higher weight to some of the features, or we treat them all equally when we compute the distance? All equally, right? So kNN doesn't have a way to say this feature is more important than that feature. All of them are considered. Okay, so all features are considered in computing the distance. Is that clear? Is that clear? Sure. Yes. Good question. 5 minutes earlier, we talked about weighted voting. And then now we are saying they are all equally important. There's a contradiction here, right? What do you think? What is weighted? What is weighted? We give the weights to something, right? What? To the nearest examples. To the examples. The weights are for the examples, not the features. It's at both are at prediction, by the way. When we compute also the distance at prediction time. But the weights are given to the neighbors, not the features. Okay? The neighbors are determined through the features. But when we compute the distances, we don't say this feature is more important than the other. We compute the distance based on all features the same way. Then we give weights to the examples. This example in the neighborhood should have higher weight because it's very close to me. Okay? Yes.
So let's say in the decision tree example, we had rain.
We had what?
The features was rain and
Yes.
temperature.
Ah.
So here the S would be rain and
Yeah, but yes, but I think the reason why you see it and you have some difficulty in seeing it is because the example that we saw in playing tennis are not all numeric. But in kNN, all the features have to be numeric because we are talking about vector space, right? All they have to have all numbers. Okay, but if the features in that example were all numeric, yes, each one will be one dimension. Yes. Actually, you can give the labels of the dimension by the name of the features. And as you said, yes, rainy here. No, but rainy was the feature value, right? The feature was the weather, I think, or what the name of the feature was. What was it? The outlook, yes. So outlook will be the dimension, and the values of the outlook will be values of the feature. Okay. If we give 0, 1, 2, 3 to the values, then that would be the. Okay. Is that clear? Type. Another issue. So this is an issue, right? This is an issue, right? Because we shouldn't give equal weights to all features, right? Now let's look at this. There's another example, another issue. Let's say that we want to classify people, maybe if they are healthy or not. Just assume for that. Assume for now. Given 3 features: height, weight, and income. Okay. Height goes from maybe 1.5 meters to 1.8 or maybe 2. The weight goes from 90 pounds to 300 pounds. Income goes from 10K per year to maybe 1 million per year. Okay? So you see here that the ranges are different, right? The scale of the values is different. Here we're talking about very small values. Here we're talking about very large values, right? What is the problem here? Why is that a problem? Now, think about how the distance is measured. When we measure the distance, let's assume for a second that we have just 2 examples that we want to compute the distance between. This is one example, and this is another example. Okay? The extremes. When I compute the distance between these 2 examples, which one of these features will have the highest effect on the value of the distance eventually? The income. Why? Because the range is very high, the difference will be high. When we square it, will be even higher. Okay, and when we add it to the others, this will be very negligible, very small, compared to the scale of the income, right? So basically, we are only looking at the income because the others are not affecting the values by much. the major factor here is the income. Is that because the income is the most important? No, because just the range of the value of this feature is higher, or the scale of that feature is larger than the scale of the others, not because it's more important. So that's an issue. kNN doesn't scale by itself. Okay, so we'll have to fix that, and we'll talk about fixing that later, inshallah. Okay, but you understood now this issue, right? Okay, another one. Some features might be completely irrelevant, completely useless. If we have, especially when we have so many features, and that's very common in machine learning. You have so many features, and you use the model. kNN doesn't consider that. It will use all features when it computes the distances, right? Whether the features are important or not, whether they are irrelevant or not, they will be considered. So of course that will affect the predictions, right? Because it will affect the getting the neighbors and thus the predictions, right? So that's an issue, and we'll need to fix it, inshallah, also later. Okay, so we laid out some issues here, right? Features are all equally important. There is no mechanism of filtering out the useless or unimportant features, and the scale of the feature values also are not considered. Yes. Not the okay. The weighted voting doesn't solve the fact that all the features are equally important. That was her question also, right? These are two different things. The weighted voting is weights are given to the examples, not the features. Still, kNN uses all features equally. Okay, so that's an issue. Another one is the scaling, and the third one is the useless features or irrelevant features that will not be filtered out. Okay, and we'll have to, inshallah, talk about that later. Okay, so we'll have to stop here, and inshallah see you on Sunday. Assalamu alaikum.